Hi, my name is Jaime Acosta, and I'm going to be presenting joint research between ARL and UTEP focused on cybersecurity deception, specifically as it can be applied on lightweight devices. There are many novel defense technologies in existence today that focus on thwarting defenders in active ways. Game theory, for example, has been used in conjunction with attack graph theory in order to determine optimal placement in networks. Low interaction honeypots are aimed at enticing lightly skilled adversaries or those using a shotgun approach. High interaction honeypots aimed at replicating entire services and systems in order to attract more skilled adversaries and to identify their techniques and procedures. These approaches, however, mostly assume that the deployed honeypots are in an always-on state and are always available, with little regard for increased resource requirements that may degrade performance, especially on lower-end non-server-like systems. Furthermore, there's little work in the field that investigates how these honeypots may affect these smaller-scale systems in constrained environments, and what kind of effects they may have when placed in existing networks and systems. So with this in mind, we present two objectives of our work. First, to enable experimentation in an efficient and portable way using open and vetted tools that have stood the test of time. We also need to be mindful of the future of system provisioning technologies, so we need to be able to connect into our experimentation, virtualization, emulation, containerization, and of course physical devices. So in summary, our immediate goal is to create a lightweight platform that can be used by the community to experiment with cyber deception technologies, and to know how these the experimentation systems perform in realistic settings. As mentioned before, Cdes is built upon many open source technologies, but the most critical is the Common Open Research Emulator, or CORE. We heavily leverage many of the capabilities, including its service-based architecture, its extensible backend API, and the graphical interface, as well as hardware in the loop, and many others. So what you're seeing here is the overall architecture of Cdes. Starting at the bottom, you'll notice that it interacts with Core through both the Instantiation Manager and the Conditional Connection Manager. The Instantiation Manager handles the starting and stopping of all Cdes components. When a user wants to use Cdes in their scenarios, they indicate this using a feature called an instantiation hook within Core. This will call the loader, which then starts the controller and all the pipeline processing of Cdes. Similarly, through a shutdown hook, Core instantiates the unloader, which will stop and clean up Cdes and any processes that were instantiated by Cdes. The Cdes controller manages a three-stage pipeline. First, the monitor engine will watch data on the system in some way. So, for example, the current time or an intrusion alert file. The output of the monitor is sent to the trigger, which essentially is where the decision-making algorithms reside. So as an example, the trigger may choose to conduct some action every 15 seconds, or possibly when a specific alert or set of alerts are encountered, it might send a command to switch to another subnetwork. The trigger sends information related to traffic redirection and instantiation to the net swapper. This component is responsible for executing the redirection activity by communicating with the Core backend. Earlier versions of Cdes used simple ifconfig interface commands, but now the newer version uses Open vSwitch to add and remove entries within the decision node's flow table. With Cdes leveraging Core's extensibility, we've added a new node type called a CC-DEC node OVS, as well as a new service called CC Decision Node. Just like any other node in Core, a user is able to drag and drop our Cdes node onto a canvas map to create the network scenario. The decision node is set to automatically have the decision service enabled. Additionally, we've programmed this node so that when connected to other nodes, it visually behaves like a layer 2 switch. Namely, interfaces it creates interfaces that do not have IP addresses. And when traffic flows through the device, by default, no actions are taken. So for example, the TTL field on a packet remains untouched. So when running traceroute, for example, or ping, the node doesn't count as a hop. The decision service consists of editable scripts for the Cdes pipeline, which by default implement some basic behavior. This behavior can be overridden directly from the GUI or from an external file editor. So I'm going to describe these components in the upcoming slides. The first component in the pipeline is the monitor. In the upper right is the default behavior. It runs a forever loop that prints the current time once every second. The output of this script is sent over to the trigger for processing. In this case, it's just an integer value. Lastly, during shutdown, the monitor accepts a signal from the controller when the scenarios stop. And this will stop any running processes that might have been instantiated from within this monitor script. So as shown here, the default behavior of the trigger is to read the monitor's output, make a decision, and send commands to the swapper. The file shown here is a dynamically loaded Python file. And this file is a subclass of a trigger parent with an overridden process data function. So essentially, to change the decision-making behavior of the trigger, a user simply needs to make changes to this process data function. Underlined here are functions that are exposed to the user in order to implement the trigger behavior. First is the function called to read a line of data coming from the monitor. If there's no data present, the loop will restart. If the data is present, then we know we're expecting time as integers because that's how we program the monitor. So we convert the data and store it into a variable called new time. Next, there's a call to get CC node numbers. This is used to retrieve all the nodes connected to this decision node. And finally, the trigger will send a command to the swapper to redirect communications between the two connected nodes every 120 seconds. So at this time, I'm going to go ahead and show a small demonstration of a scenario that we've developed that's based on a Suricata intrusion alert system. Here you'll see that I have the Common Open Research Emulator open, and I have a scenario that I built earlier. The scenario consists of a legitimate network, which is here on the top side. You can see there are 4 nodes here, a legitimate client, N3, N4, and a legitimate server. Down on the left side, we have an untrusted node, which is on an external network. This external node is connected to a decision node. And as you can see at the start of this scenario, the decision node is indeed connected into the legitimate network. And you can tell this by the blue lines. On the bottom right, you'll see we have a yellow line that's feeding into our Honey network. So this means that there's no real connection here. It's essentially severed. And eventually what's going to happen is we're going to redirect the untrusted node's traffic from the legitimate network into the Honey network. One thing to take note of here is that our node in the legitimate network as well as in the Honey network both have the same IP address, and they also have the same MAC address. So the way that we configured the scenario to run Cdes is first by declaring a few hooks. The first hook is our start Cdes hook, and essentially what this does is it calls the Cdes loader. So this is what instantiates Cdes. We also have a Suricata start runtime hook that also begins when the scenario begins. And essentially what we've defined here is for Suricata to execute with a specified rule. So what we also did here is we create a rule, a few set of rules actually. Here you can see that we have 3 rules that are essentially watching for ICMP packets, and if any of those are observed, then an alert will be generated in a file. And lastly, we have our stop hook, and essentially what this does is it kills Suricata whenever the service is stopped. Okay, so a little bit about our decision node. I'm going to go ahead and double click this to see the services that are running. You can see that we have our decision node service. To look deeper into the configuration, you'll notice that we have a monitor. What this monitor is doing is essentially reading output from our alert file. This is where, again, Suricata is writing any alerts that match any of the rules. Second thing that you'll see here is a trigger file. And what you'll notice is that this is watching for alerts that have a specific identifier, in this case 110001. If that indicator or identifier is seen more than 20 times, then the swapper is going to be invoked, and it's essentially going to redirect the traffic to the Honey network. And just very quickly, the last item here that's associated with the service is the setup for OVS, which is the underlying technology that we use for the swapping behavior. So I'm going to go ahead and run the scenario. When all the green brackets disappear, that means that the scenario is fully begun. Next thing I'm going to do is I'm going to look at my alert file so I can see whenever our intrusion detection system generates any alerts. So I'm going to use the tail command. And I'm going to watch the fast.log. This is where we'll see our alerts. And at the same time, I'm going to open a terminal on my untrusted node. Let me reopen my alert file. And I'm going to go ahead and start pinging a node within the legitimate network. Specifically, I'm going to ping 10.0.2.2, which is the first interface on our N4 node in our legitimate network. So as soon as I send those ping requests, and you'll notice that I'm getting a few alerts here on the top side, and after 20 alerts are observed, you'll see that our blue line that was feeding into a legitimate network from our decision node is now yellow. That means we've severed that communication, and now we've enabled a connection to our Honey network down here on the bottom right. So just to show you that we still have connection to a 10.0.1.1 gateway node, I'm going to go ahead and ping that. And you'll see that I still have connectivity here, which means that this untrusted node is now fully connected into the Honey network and not connected to the legitimate network. We wanted to determine how Cdes performed when placed in line on a network, so we created the scenario C here. Created a scenario with 3 hardware-in-the-loop interfaces. These connect external devices into a core scenario. Core was running on a laptop, the specs that you see here on the left side of the slide. In the scenario, on the left, we connected a physical laptop. This served as our scanning machine, which communicates to the recipient nodes through the core scenario. The recipient nodes can be seen on the right. The first is a physical laptop. The second is a core node, or a kernel network namespace. And the third one is one of 2 possible virtual machines. A Cdes decision node will enable only one of the 3 connections you see to the recipient machines at one time. So we first tested how much delay is introduced when we have a laptop running core in between 2 nodes. We ran the pings at 10 per second for 1,000 seconds. The top graph shows the delay associated with round-trip pings in milliseconds. On average, the time it takes is 0.39 milliseconds, with a very small standard deviation of 0.04 milliseconds. The bottom graphs show the delay when we have our Cdes laptop in line and as we switch across recipients. With a namespace, the delays are just a bit higher than without the core laptop. This is because the packets don't leave the laptop in this case. The namespace is a node within core on the laptop. The pass-through to a physical recipient and HoneyVM cases are similar to each other, except that the standard deviations for the pass-through is a bit lower. So still generally the delays are relatively close. So in summary, we know that there are delays, but they're small and it's unlikely that they'll be noticed, especially in more complex networks when not studied side by side like we have here. It's also noteworthy that we also tested with core running in a VM. We had similar but less stable results. The question that we sought to answer next is, can we match the delays of the namespace case to be closer to that of the others? And generally the answer is yes. In the top graph, you'll see the delays side by side when using switching dynamically between the recipients. The namespace case stands out, so by using a feature in core to add intentional delay to a link, we were able to better normalize the results. For the results on the previous graph, we used the case where all recipients were always on. Cdes only had a switch between them. So this consumes many resources, and this led us to our next question. We wanted to test the performance when we instantiate VMs on the fly, or on demand. So we tested with two cases, when the VMs are in a save state or at rest, and when the VMs are in a paused state. The main difference between these two is that if paused, the VMs still consume RAM, but when they're saved, they must be loaded back into RAM. The results here show that when using pause resume, there aren't any noticeable blips. When instantiating a small VM like TinyCore, there's also very little noticeable delay. However, when restoring an Ubuntu 20 VM, there is a noticeable delay, as you can see there. So we learned that depending on system constraints and needs, a user would have to choose a solution that balances between delays and resource availability. Next, we wanted to further characterize the system utilization. So as expected, when using the pause resume option, the memory utilization is constant because the VM is kept in memory when paused. However, CPU utilization during the pause and resume operation remained pretty low throughout. With the save state and restore cases, less memory is used when saved, but CPU jumps when instantiated in order to load the VM into memory, which is the cause for the delay that you saw on the previous slide. So to summarize what I've shown so far, we know that we can save resources by instantiating honeypots in an ad hoc way, and we know that there are trade-offs depending on which approach we use. So next we want to know if Cdes can swap and instantiate, in particularly using pause resume, fast enough to thwart a real network scan using the Nmap tool. We started by dissecting an aggressive Nmap scan, and here we show a few of the steps involved in this process. First, Nmap sends a set of packets to identify if a host is up. This is the host discovery stage, and this completes very quickly within 0.01 milliseconds. Next, the recipient or victim of the scan will reply. The total time for this is roughly 0.3 seconds. Finally, based on the response, Nmap will now know that the host is up, and it will continue by attempting to look for open ports by using TCP SYN packets. If there's a response from the recipient, then Nmap knows that a port is open. So roughly, the total time taken for this process is 0.44 seconds. In order for Cdes to succeed in thwarting an Nmap probe, it must be able to start and switch to a honeypot before the service probe begins. This is roughly within 0.3 seconds. We tested with several virtual machines in addition to the TinyCore and Ubuntu 20, and found that Cdes is effective in all cases but two. In the case of Ubuntu 20 and Ubuntu 18, the delay was slightly longer than 0.3 seconds. However, it's worth noting that Cdes succeeds in these cases when Nmap is run without specifying a particular port. In summary, Cdes is a novel experimentation tool that allows researchers to test deception algorithms and techniques in a standalone and/or within a network. We also include many demonstrations with Cdes out of the box, including the one I showed previously in this presentation. In the future, we'll look into integrating eMain into our toolset to allow for higher granularity physical layer representation. We're also looking at ways to identify known scanning tools and services of interest in order to tactically instantiate types of honey nets on small-scale devices in particular. So I hope you enjoyed this presentation. Thank you for your attention.